Hello community, it is a beautiful Friday and those are the latest research publications on AI. Let's start here with an introduction to reinforcement learning. The fundamental concepts and practical application on 24 pages. Beautiful. If you're new to reinforcement learning, this is it. This paper demystifies the comprehensive yet simple introduction for beginners by offering a structured and clear pathway for acquiring and implementing real-time techniques into reinforcement learning if you want to know how to cope here with all the different agents. Now, reinforcement learning is our first topic. So let's jump right in and let's have here the classical reinforcement learning. And August 15, there was a new publication on a new way of reinforcement learning, the intrinsic reward enhanced context-aware reinforcement learning for a specific human AI coordination. And this is from Australia. Deakin University, Victoria, University of Adelaide, South Australia. Hello Australia, so great to see you. And they say in human AI coordination scenarios, the human agents usually exhibit an asymmetric behavior that are significantly sparse and unpredictable to those of the AI agents because humans are simply crazy. And we have impulses and we have communication that may change in the tone and whatever in the logical argumentation. So there are problems. And they say, hey, we propose an intrinsic reward enhanced context-aware reinforcement learning algorithm. So if you want to learn here about a new reinforcement algorithm, this is great. They give you here a beautiful overview. But we jump here into another reinforcement paper of today, August 15, 2024. And we talk about safe reinforcement learning. And here in this publication, they do here the safety aspect here with a meta-gradient-based hyperparameter tuning. Now, let's start here. Reinforcement learning, one of the most important paradigms for learning to control physical systems. A major shortcoming in reinforcement learning is the need for exploration and extensive trial and error. And there something can happen. And we need a safe reinforcement learning methodology so that the system does not damage itself or incur some heavy cost to the user if the robot arm destroys something in the surrounding. So, safe reinforcement learning methods to aim to address this issue by optimizing the policies such that it is compliant with the constraints that we impose. Now, most common approach in safe reinforcement learning is through the Lagrangian methodology, specified under the constraint Markov decision process framework through defining threshold for those constraints. The multi-objective optimization problem is converted to constraint satisfaction and is solved by casting it into an unconstrained problem using the Lagrangian methodology. If you want to have a deep dive, this is a beautiful work. They tell you everything about the constraint Markov decision process. Then, Bellman equation already showed you. Then they have the soft actor critique optimization here of a stochastic policy framework. I also showed you here in one of my last videos. And then they give here the detailed description of the meta-gradient optimization. And they show here the computational graph for their specific optimization problem. Real nice paper. They give you also the pseudocode. They give you here the defined Lagrangian that they use in their calculation. Highly recommend the paper. Now, talking about here safe reinforcement learning, this last paper was just a very particular brand new methodology. But if you want to have here a look back, what is available, what is the review of safe reinforcement learning, what are all the methods, the theories and the application, I have found for you here a publication from the end of May 2024. Yes, I know it's already 3 months old, but it is really nice because it's a review of the safe reinforcement learning provided by theoretical application analysis. And if you have a look at it, almost 100 pages, and give you a real nice overview by the Technical University of Munich, Peking University Department of Informatics, King's College London, Tongji University in China, and the University College London, UK. Beautiful. And there you can dive in and they give even some code. So if you want to learn about safe reinforcement learning, safe policy, safe complexity, application, safety benchmark. And at the end, I think this is the paper for you. Let's go on and let's increase the complexity a little bit, because now we are talking about reward machines, and we talk about maximally permissive reward machine. We have here Utrecht University, Open University, the University of Aberdeen. And you might ask, what is it? A reward machine were introduced as a way of defining temporally extended. This means non-Markovian relative to the environment, task, and behavior. But we wanted to show you, where is it? Yeah, here. They give you a real nice introduction in reinforcement learning, a simple Markov decision process. They explain here the optimal policies for you. They show you what is their value function. Then they go here with the label Markov decision processes. And then I would recommend here chapter 2.3, where they show you reward machine. And they give you a beautiful definition. What is a reward machine? A tuple where this and this and this. Beautiful. So I will enter this because, yes, you got it. We then go here to a Markov decision process with a reward machine, and then we jump to symbolic planning. And this is interesting, and I will focus on other publication also here on the combination of a neural network and symbolic logic. So here we have at first here the symbolic planning domain, and they give you a real nice introduction into the topic. They show you here even some pseudocode. So if you enter this topic, I would recommend this paper to you. Now, let's go on. And you know, we are here about the rewards, about the future rewards of multi-agent system, multi-AI systems. And then we have the problem, if we have here temporarily decomposing here the sum of the future reward estimators. You know, normally we have a sum of those. And here, this scientist from University of Southampton, King's College London, they go now a step-by-step approach, and they have a look exactly about the temporal reward decomposition. Because they argue, if I know exactly, if time step 1, time step 2, time step 3, I know exactly what is the temporal reward structure, and I do not have simply a sum over all the events, it will help me to fine-tune here the temporal reward structure. So they argue this unlocks here the novel explanation of the agent behavior, and through this temporal reward decomposition, we can estimate when an agent may expect to receive a reward, the value of this particular reward, and the agent's confidence interval in receiving it. So real nice. So we go now from a sum of a reward, we go now to the specific time steps, and they give you a real nice interpretation, and you can follow along in this paper. What is real funny, and I really recommend this is now solving here a Rubiks Cube using its local graph structure. So Chinese University of Hong Kong and Trinity University, they had this beautiful idea, and they say, hey, you know a Rubik's Cube, 3x3x3 single player combination puzzle. And now we use reinforcement learning policies to find here on a graph structure the shortest path to the solution. And to be able to do this, they develop a new heuristic. And they say, okay, the idea is simple. The Rubik Cube can be represented as a graph, where the states of the cube are simply the nodes and the actions are the edges. Drawing now on the graph convolutional networks that we know, they design a new heuristic, a weighted convolutional distance for the A-star search algorithm to find the solution to a scrambled Rubik Cube. It utilizes all the information from the neighboring nodes and convolves them with attention-like weights, which creates a deeper search for the shortest path to the solved state. What an intelligent application here, a simple Rubik Cube that we can imagine, and we use here the graph structure and the A-star search algorithm. Now, I know you might say, hey, but you already showed us here the A-star and the Q-star reasoning, complex multi-step reasoning process. I know, but this is done on a Rubik Cube, and therefore I really enjoyed this. Okay, next one is, evolving, and you say, unbelievable, this was also published today, yes, August 15, evolving now the A star to an efficiently solve here a K shortest path problem. And this is not just about one path, but K shortest path problem. So we increase the difficulty a little bit more, and we have a look at this particular A star extension to multiple paths. So if you're interested in this, a very nice paper, explained beautiful in detail. Again, what is a directed graph? Give you all the explanation, yes, definition. Directed cyclic graph, all the definition. You can really read this and enjoy this, and it gives you an excellent introduction into the topic. However, I even have here the original, the very first idea of A star. And look, it goes back to July 1968. I wasn't even born at that time. Can you imagine this? And we have here an article, a formal basis for the heuristic determination of a minimum cost path. And in 1968, they have here the problem of finding path through graphs. So if we think today that AI is special, forget about it. And you know who wrote this? This manuscript was received in 1967, and the authors are with the Artificial Intelligence Group of the Applied Physics Laboratory, Stanford Research Institute, California. Isn't this fascinating? I said, wow, we have 1968, the search A star algorithm already here. I think this is really the first time that I found it in the literature. So if you think here that this is a new research, no, my goodness, it's really old. But read the paper, you're gonna smile at the different perspective people had for AI research in 1967. Beautiful. So let's jump back to today, and we go now here for the graph embeddings. We use here a knowledge graph. We construct the embeddings for the task of a link prediction. Plus, we have here a little bit more complex the task. We go for predictive multiplicity of knowledge graph embeddings in link prediction. University of Stuttgart, Bosch Center for AI, Cardiff University, University of Oslo, and the University of Southampton. And you might say, okay, what is it? What is the problem? There is now this multiplicity problem, quotation mark. So what is it? Multiple knowledge graph embeddings can perform almost equally well for link prediction, yet suggest conflicting predictions for certain queries, termed here the predictive multiplicity in our literature. And you might say, how is this possible? Well, the explanation is rather easy. Given the non-convexity of the training problem, the same knowledge graph may lead to various knowledge graph embeddings because of the conversion of the training in different local minima. So you see what happens? They just drop into different local minima, and they are not able to find here the global minima configuration. Therefore, there's now a new idea, the predictive multiplicity here, to handle exactly this problem. A very nice publication, explain here, really nice knowledge graph embedding, how does it work, what are the formulas, and I think the speciality here of this paper is they use here a social choice theory. Social choice theory studies collective decision-making processes where the individual preferences are aggregated to determine a group overall preference. And you can do this with humans, and you can do this with the decisions of AI agents. So this is a kind of a funny study because they use here our social choice theory to come up with a decision-making process for a real complex multi-agent AI system, if you want. Great. Now, talking about the complexity of AI, let's stick here with the knowledge graph and let's apply here, maybe we add a little bit of an LLM, that's much more interesting, and we apply this here to an industrial problem, and we talk here about supply chain. And sometimes here for manufacturing processes or whatever, we have here a study by the University of Cambridge, and they say enhancing the supply chain visibility with knowledge graphs and LLMs. So what they do, they are here simply, they want to examine here the exact supply chain and a mapping of those. If you read this, I think there's a beautiful image here. So you have here a manufacturer and they have here tier 1, tier 2 and tier 3 suppliers. But you see tier 1, of course, you know them, but tier 2 are already somewhere, and maybe tier 3 suppliers, these are just the rare earth, for example, or some special materials that have to be processed here by our tier 2 suppliers. They are hardly visible, so we cannot know anything about how this value chain or how this supply chain configures itself. So what they do, they use here a graph structure with an LLM. They load here all the publicly available data, or maybe just company-specific data, articles, Wikipedia pages, web pages. Then they have a name entity recognition and a relationship recognition. They build here a beautiful graph with the help of an LLM, and therefore they get an enhanced supply chain visibility. So if you want to know either inside of the company or outside of the company of whatever legal requirement, you want really to know here the suppliers that go maybe on a global network, and you have to scan here the whole internet or whatever to find out who are the tier 1 supplier or the tier 3 suppliers. This is rather easy, and this is a beautiful framework, a beautiful application here by the University of Cambridge to really see where are all the materials, for example, coming from if you do some electric vehicle. Now, next publication is now a little bit more complicated. Chinese Academy of Science, Beijing. We have here a novel online Neuro Symbolic framework for event prediction based on LLMs. So if you're not at all familiar with this, never mind. So we just look at this. So we want to have main event is event prediction. This is it. And we use here an LLM, but maybe we do not use only an LLM, but we also use here a mathematical logic framework, a neural symbolic framework that we combine with our LLM so we can predict here events in the future, given we have the history of all the relevant events and data and facts. So, officially in the realm of event prediction, temporal knowledge graph forecasting, as is the official wording, stands as a pivotal technique. Previous approaches faced the challenge of not utilizing experience during testing and relying on a single short-term history, which limits the adaptation to evolving data. And the authors here introduce a new online, so real-time, neural symbolic event prediction framework, which innovates by integrating dynamic causal rule mining and dual history augmented generation. And dual history simply means they go for the real medium-term history and for the short-term historical contexts. So if you compare this here with a simple ICL in context learning, where you have just some historical data in your training data set, or you have here a much more complex and much more detailed, going much more back on the historical data, they have here this novel online neurosymbolic framework for the event prediction. Simple example, they say, hey, we have here a quadruple. This is, for example, Angela Merkel visits China on a particular date. It's clear what this means, this quadruple information. And then they simply ask, when will the next event happen? Now, you have to know now everything about the history, why they met, what was the purpose of the visit, what was discussed at the visit, is this person still responsible, who is responsible now? On the other side here of the table, what is happening? How has the geopolitical situation changed? Is there a visit necessary? What are the goals of the visit? So you need all the historical data, and you have to find out, can we deduct something from the historical, from the near historical and medium-term historical data? And this is what they call here a dual historically augmented generation, a bi-branch receiver. Real nice idea, but of course you have to have access to all the relevant data, because a problem here might be that here the causal rules that are found might not be the real reason why a diplomatic visit happened. So temporal knowledge graph forecasting, a very hot topic in AI research, but given the complexity, I would say you need a lot of data so that here the causal rules can really be found and understood, and then you have here a dynamic system dynamic that you can map on to the LLM. Let's go on to the next one. Oh yeah, that's the title. So we are here still at, and I prepared this for you, temporal knowledge graph. Now you know what this is. And now we do an extrapolation reasoning. So now we do not just want to have here a causal chain of events that we extrapolate, but now can we do this here for the complete reasoning path? And we do this here by a causal enhanced graph representation learning framework for improving here the temporal knowledge graph extrapolation reasoning. So you see the complexity increases slightly even more and more, and you see it is not anymore just the base model, I don't know, a 3.5 Sonnet or a Gemini model. No. Now the combination, what the AI community is achieving globally, is simply amazing if you read this paper. And those papers are just here a very minuscule selection of I scanned more than 300 AI research papers that were published today, and those are the papers that I wanted to show you and tell you, look at what amazing content is currently done by the AI community. But let's come back here. We have here Southwest University, China, School of Information Science and Engineering here, Jiaotong University, China, beautiful. And they go now into, again, this temporal knowledge graph reasoning. It's gaining attention for its ability to extrapolate new events from historical data, just showed you this in the other publication, thereby enriching the inherently incomplete temporal knowledge graph. Can you imagine the complexity of the knowledge graph if you want to analyze when a state leader is going to visit another state officially, a diplomatic mission? Do you know how many data you need on economy, on all the other factors that are important here that two state leaders meet? Amazing graph structure is going to emerge. So existing graph-based representation learning framework have made significant stride in developing here those representations for both the entities and the relation embeddings, but there's a notable tendency that these models to inadequately learn biased data representation. So there are data, but those are not the real data that are the real causal, the source of the motivation. So this leads to incorrect prediction based on false correlation. So how you want to address this? They try, in my words, simply to use here a filter. So they have here a framework, introduces causal structures in a graph-based representation learning to unveil the essential causal relationship between the events, ultimately enhancing now the task performance. And they try to find here the confounding representation. Those representations that are not really helpful, maybe you can call it a little bit crazy representation, but you should have them, but give them a specific scoring so you understand that maybe in the first 5 runs, there's a representation that might not be helpful, but don't put it as completely aside, but keep it just with a very low probability density. So you see, amazing research is taking place in this area. Okay, next one is here training LLMs on the knowledge graph. You ask a lot, how is now this possible that we have our LLMs and the knowledge graph? How do we interact here together? And this study is here, August 14, looks at here hallucination and the detection of hallucination in LLMs that were trained on knowledge graphs. You see, this is here work from Google DeepMind. What can I tell you? Control the training. We construct a knowledge graph-based data set and use it to train a set of increasingly large language model. And we find that for a fixed data set, the Google data set, larger and longer trained large language model hallucinate less, which is real nice, but unfortunately for all our GPU poor little beings, because this means that our huge LLMs hallucinate less. However, hallucinating on less than 5% of the training data requires an order of magnitude larger models. So the jump is significant if you scale this up, and thus an order of magnitude more compute than Huffman reported as an optimal configuration. So given this costliness, we study how hallucination detectors depend on scale. Interesting if you want to know here about knowledge graph, LLM, and hallucination in those systems and how they scale up if you use bigger and bigger models. But the information I took is for a fixed data set here, a specific data set focused here on hallucination detection, larger and longer trained LLMs hallucinate less. Okay, we have to live with this. On we go. The next one, we already stick here to knowledge graph embedding. And now we go here for AnswerSet prediction. So we are here in logic, and we go here for conformalized AnswerSet prediction for knowledge graph embedding. I mean, of course, University of Stuttgart, Bosch Center for AI, Cardiff University, University of Oslo, University of Southampton, and Eindhoven University. We have knowledge graph embedding. They are typically used to answer queries by ranking here all potential answers, but those rankings, that we have often lack a meaningful probabilistic interpretation, because lower ranked answers do not necessarily have a lower probability of being true. Think about this. This has some massive influence. So this limitation makes it difficult to distinguish plausible from implausible answers, posing here challenges for the application of knowledge graph embedding methods in high-stake domains like in medicine. Because the ranking is now for a particular solution, it has a real low ranking, it doesn't mean that it is not the true solution or that it is one of maybe the best solution, but the ranking is a little bit of decoupled here. So we address this issue by applying a theory of conformal prediction that allows generating answer set which contain the correct answer with a probabilistic guarantee. So imagine this simple: you have now an answer and you have an error bar attached to all your rankings. So you know exactly here the probability density that this particular result has. If you want to learn this a little bit more in detail and in a much better formulation, it's a real nice paper. Again, they start here with knowledge graph embedding. Conformal prediction is a general framework for producing answer sets that cover the ground truth with a probabilistic guarantees. They recover here all their work. They show you how it's done. Knowledge-based answer set prediction, problem definition, there's everything that you need to know. Let's come slowly to an end. We go here now with design choices in multi-shot ASP. AnswerSet programming is a well understood and established problem solving and knowledge representation paradigm, become more prominent amongst the wider audience due to its multiple applications in science and industry. And the constant development of advanced programming and modeling techniques extend this toolset for developers and users regularly. This paper compiles and demonstrates different techniques to reuse the logic program parts, the multi-shot, by solving the card game Snake. And this is interesting because a victory can be assured by solving the NP-hard problem of Hamiltonian cycles. This is real nice. If you are into this multi-shot ASP logic, highly recommend this paper. Yes, we know this. Is there something I wanted to show you? AnswerSet programming, yes, you are familiar with ASP. They apply it now to the Snake problem. Yeah, they have here whatever. Klingo provides here an API to assess the functionality of an ASP program within the imperative language such as Python. Yes, graph, paths, and Hamiltonian cycles, and this is our game that we applied for. And I like this simple explanation where I have a simple game. It helps me to understand here a little bit more what is going on. Beautiful. Let's go on. Yes. Last time you asked me about AnswerSet. Can you give us here an idea what is this AnswerSet programming? I found this article. I'm not sure that I'm allowed to show you this, but maybe I give you just the PDF here in the description of this video. This, I like this one, AnswerSet Programming at a Glance. This is an old one. This is from December 2011. Can you imagine this? But I think they give you an excellent overview. Can solving hard computational problems be made easy? Yes, yes, yes. AnswerSet Programming fits the bill, and they give you here a beautiful explanation. They show you how it is built. I showed you a little bit in my last video. And give you beautiful examples to really get it immediately. So I would recommend you this review article from 2011. But if you like to go with other explanation, go with whatever you find. Maybe you ask your AI system, your Claude, your Sonnet, your Gemini, or whatever. I think there are for sure some beautiful explanation of AnswerSet Programming. And in this publication from the Department of Computer Science at Leuven, Belgium, they are talking now about scaling learning for neural probabilistic logic systems. So I ask here my ChatGPT, just to make it clear here, the general approach. We have two possibilities. We go on the one hand for the Neuro Symbolic Ai. This simply combines a neural network with symbolic reasoning system, focusing on integrating the strength of neural network, pattern recognition, learning from data with symbolic AI, especially for logical reasoning and knowledge representation. It includes here a variety of methods as AnswerSet Programming that we were just talking about, rule-based system. And the second one is neural probabilistic logic system. Careful, it's a little bit different. This is now a subset of our general Neuro Symbolic Ai, and it combines now our neural network architecture with a probabilistic logic structure. This is really interesting because it's focusing on adding the robustness and uncertainty handling of a probabilistic logic to the learning and perceptual capabilities of the neural network, and it tries here to manage uncertainty or noisy data while still providing some logical, interpretable reasoning. So this is now really the, let's say, the most complicated part of today. If you want to dive into neural probabilistic logic, I recommend this paper, August 15, 2024. So therefore, we have neural probabilistic logic system. They follow the neuro symbolic paradigm by combining here the perceptive and learning capabilities of neural network with the robustness of probabilistic logic. And they here develop a new methodology. They develop here the explain, agree, and learn method for an improvement. They give you here in detail what they're doing. They have a very nice introduction. They have a very nice representation here of the background. They explain exactly what they're doing. They have here definition 1, 2, 4. Careful for definition 4, just a hint if you want to read it. Real nice paper, I recommend this. So you see the possibility how we apply AI system, how we combine LLM with now neural probabilistic logic system. This synthesis, this symbiosis is so important. And therefore, whatever we know about the LLM is crucial importance because the error propagation from the LLM into a neural probabilistic logic system, we have to minimize those hallucination quotation mark that we have the full power of our neural probabilistic logic system. So this was it. This was here the last Friday recording. So we have now 1 week of the latest AI research paper. I hope you found it not overwhelming, but interesting. You discovered some new parts. Maybe like I left my bubble. I went out into the other space outside of the bubble where I had no idea what to expect. I discovered there are so many beautiful applications by the AI community. I would like to show you in my next video what the AI community is achieving. It is not about a system by Microsoft or by Google or whatever. It is about how we apply those AI systems, how we combine it with logic system, with neural probabilistic logic system, where we are in the research and where we move on from here. I hope you enjoyed it, and it would be great to see you in my next video.